All right, so here we are again. So we, as you know, are in sort of in the early part of chapter 2, our discussion about limits. And limits really, this is the only chapter that will really use them, except in chapter 3, we'll use them to define the concept of the derivative. But it's kind of a specialized topic. It's important to understand how limits work, but we're not going to use them that often down the road. But it is a very useful idea, and we can use it to derive important results. So let's just go back to where we left off, and which is with the limit rules of limits. Okay, so in other words, if you are asked to calculate a limit, there are several rules that can be applied here, and they're all pretty straightforward. There's nothing the least bit surprising in these rules. In most cases, in many cases, you're essentially substituting constants into the function that you're taking a limit of and seeing where they are. The complications arise when we end up having infinity or negative infinity, or we may have a function where direct substitution leads to a result like division by 0. And then we have to figure out what else we can do to solve this problem. Okay, so, but for the most part, limits are very straightforward. Now, we're actually going to see more complicated ones in the next chapter. The cases where, for example, you wind up with a ratio of something ridiculous like infinity over infinity. In cases like that, there are techniques we can still use to come up with a result. But we don't know how to, we do not yet know how to implement those techniques. So first, let's focus on the basic cases. So we started out yesterday by looking at the case of the limit of a constant. And since a constant doesn't change, the limit, no matter what x is approaching, is simply equal to that constant. Okay, so no matter what k is, and no matter what a is, the limit of k is just k. All right, so that's one of the foundations of what comes next. So here's a simple example. The limit of 3 as x approaches 0 is just 3. All right, now, once we introduce a variable, though, let's say that we have the limit of x raised to some exponent n, where x is approaching a, all we have to do is plug in a for x, and we'll have a result. And it's really just that simple. Now, part of the reason for that is because with a function like this, it's not possible to run into problems like division by 0 or possibly having the square root of a negative number. So we don't have to worry about the existence of these limits. So all we have to do is go ahead and plug in the correct values, and we'll have a result. So let's say, for example, our function is x squared, and we want to know what is the limit as x approaches 3. Well, by plugging in 3 for x, we end up with 9, and that's because if you draw a picture of this function, oops, hold on one second. Okay, well, this is a fairly easy function to draw. It's just a parabola that touches 0, 0 right here. And so this is y equals x squared. And so here's 3. I guess. All right, maybe that's not the best choice. Hold on. Let's say this is 3, and this is, of course, 9. So the idea here is that as x approaches 3 from the smaller values, which we've already seen from yesterday, we can write this as x approaches 3, and we use a little negative sign here to indicate that it is approaching from the left or from smaller values. And coming from this direction, we can write that as x approaches 3 with a little plus sign, which means it's coming from the larger values. And so no matter how you approach 3, you're going to keep getting closer and closer to 9. Okay, and so that's why the limit is 9, because no matter how close we get, eventually we'll find ourselves with a value of y equal to 9. All right, so that's a very straightforward example. Now, there's other cases that are also very straightforward, like something like this. If there's a constant in here, we can essentially just factor it out. Okay, so in other words, if you had the limit of, let's say, the limit as x goes to 0 of, let's say, actually, let me make it simpler. Let's make this 1 of, I don't know, 3x cubed, let's say. This can be rewritten very simply as 3 times the limit as x approaches 1 of x cubed. And now here, because this is x cubed, we can follow this case, x cubed would have a value of a to the 3rd power. So we'll end up with 3 times 1 cubed, or just 3. Okay, so the constant is just something that we can move outside of the expression and evaluate that at the end. Once we've calculated the limit, we can then multiply by that constant. So it's kind of like this could be rewritten like this. You can evaluate this x squared followed by multiplying by 3. And so we end up with the same result. So we call this the constant multiple rule because we're multiplying the expression by a constant, which implies that something like this, the limit as x approaches a of k x to the n power, once we substitute a for x, we end up with ka to the n power. So let's say we had the limit as x approaches 2 of 3x to the 4th, then it would just end up being 2 to the 4th, where we're literally just plugging in 2 for x. And so 2 to the 4th is 16. And so we end up with 48. Okay, so again, it's a very straightforward process here. As long as we're dealing with well-behaved functions, like this is actually a simple example of a polynomial, then we're going to have an easy time calculating the limits. Later on, when we start looking at the limits of more complicated functions, and especially the trig functions, then it starts to get a little messy. All right, now sums and differences. Again, very straightforward. The limit of a sum of 2 functions can be rewritten as the sum or difference of the 2 functions' limits. And so that makes it very easy for us to calculate the limit. So you notice how I've got plus and minus listed there. Either way, in the first case is a sum. The limit of the sum is the sum of the limits. In the second case, the limit of the difference is equal to the difference of the limits. Okay, so again, a very straightforward idea. So let's take a look at a quick example on the next slide. This will be a limit of a sum. And so you can see the limit of 3x to the 5th plus 2x to the 4th. I can rewrite this as the limit of 3x to the 5th plus the limit of 2x to the 4th. And by the way, in both of these cases, we have to have x converge to the same value. And as we saw before, because these are simple polynomials, all I have to do is replace the x's with 3 and solve for them. And you can see I end up with 891 in this case. And by the way, if you're not sure, you can always go to Symbolab. I've been working with it a lot lately. And, sometimes it's not always the most straightforward package to use, but what I discovered in this case is it does have a separate button here for limit. What I discovered is that if you just type the word limit, it's not going to work. Here's what you have to do. Suppose I wanted to reproduce this one. Okay, I would have to type limit. Now here you see how it asks you what you want x to converge to. It assumes that you mean infinity unless you tell it something else. So in this case, it converges to 3. So you can just change that right here. And so then you've got the 3x to the 5th. And then you've got 2x to the 4th. And then you just say go. Make sure you hit the go button. Otherwise, it won't understand what you're doing. And then in this case, it's right there. And often what they're going to do is they're going to help you understand exactly how they got there. Not always. Sometimes they're better than others, but what they're essentially telling you here is that all we had to do is plug in the value 3 for x, and we would end up with the correct value. I don't know if you can actually graph. Oh, yeah, you can. All right. So they're saying this is what the function actually looked like. And when x equals 3, the function has a value of 891. So this is clearly the limit, because whether you're approaching from the left or the right, will eventually end up with the function will be worth 891 when x equals 3. Okay. Now the product rule is very similar to the sum and difference rules. The limit of a product is equal to the product of the limits. It's that simple. Now, sometimes it'll turn out that using these techniques will actually make it easier to simplify our results. So, we're not just doing this for the fun of it. Sometimes it's very helpful to have these properties so that we can simplify our results. And whenever that's possible, we always want to simplify whatever we're doing. Okay, so here's an example. So here, the way I wrote it out, it should be clear. The limit as x approaches to a 4x squared times 5x cubed could be rewritten as the limit of 4x squared times the limit of 5x cubed. In both cases, of course, x is approaching 2. And then once again, we just plug in the 2 for the x, and we solve, and we end up with 640. And so, of course, we could go to Symbolab if we wanted to and confirm this, but this is correct. Now, this next one, the quotient rule, as it's called, is pretty much exactly what you'd expect. It turns out that the limit of a quotient is equal to the quotient of the limits. The only thing, of course, we have to watch out for is that it must be the case that this limit cannot be equal to 0. If it is, there could be a workaround. We'll see later on. It still may be possible to find the limit, but it's going to be a lot more challenging, and it may not exist at all. So as long as we don't have division by 0, all we have to do is break this up into a ratio of 2 limits and solve for this algebraically. All right, here's a good example. The limit as x approaches 4 of 7x squared over 3x cubed equals the limit of 7x squared over the limit of 3x cubed. And once again, we simply plug these in. And we end up with 112 over 192, or you can write that as 0.583. Now, in a case like this, of course, you could, if you really would have preferred to do it this way, just simplify, and you'll see that you'll end up with 7 over 3x. And then technically, you're still doing the same thing. I mean, it's the limit. X approaches 4 of 7 over the limit as x approaches 4 of 3x. The numerator is just 7 because that's a constant. And here we have 3 times 4. Yeah, so I could have reduced this a little. 112 over 192 is just 7/12. So we still end up with 0.583. So there's usually more than one way of solving any type of limit. Just in general in math, there's almost always multiple ways of solving any type of problem. What you normally try to do, of course, is do the one that is the most straightforward, because that minimizes the risk of mistakes. All right, so there's only one more. Okay, good. And then we get to do the more complicated material. So here, now this one's kind of interesting. Yeah, it looks like there's a typo here. No, oh no, there's not. Sorry, my mistake. It's not a typo. This is what it's supposed to look like. Because what it's saying is that the limit of f of x to the n power, you see what we've got here is that we're taking the limit of f of x and then raising that to the nth power. But this only works if n is strictly positive. For a second, I thought it was the same thing, and I realized no. The brackets here tell me that in this case, I'm taking the limit of f of x first, and then I'm applying the exponent, whereas here, I'm actually applying the exponent, and then I'm taking the limit. So this is known as the power rule. And let's look at an example of this. So we'll start with the limit of x approaches 1 of 5x all raised to the 4th power. So I'll apply my rule, and then inside the brackets, I'll calculate the limit of 5x as x approaches 1, which you can see what I've done is I've replaced the x with a 1. So I end up with 5 to the 4th power, which turns out to be 625. Now, had I chosen to do so, I could have done this. I could have just said, well, listen, if I raise this to the 4th power first, before I take any limits, it's just 625 x to the 4th power. And then when I plug this in, I'll still, of course, get the same result. So it just demonstrates that we did it correctly. All right, so those are the basic rules. And, most of the cases you'll run into will follow one of these rules very nicely, but soon enough, we'll start running into cases that are a little bit more complicated, especially when zeros and infinities get involved. Then you don't know what might happen. But here, for straight ahead algebraic expressions, these are pretty much all polynomials, the results are very simple. All right, now B, 2B, let's see what's going on there. Now here we're just making the case that given all those rules that we just defined, any algebraic expression in principle could be broken up so that we can apply these rules. And we may have to apply them several times, but ultimately we'll get the correct result. So we'll start with an extremely simple case, something like this. What we can do is we could evaluate it directly, and we'll end up with 4 times -3 plus 2. But it might, depending on the circumstances, it might be easier to do it this way. What if we were to break it up into 2 limits? Now, of course, we already know that we can do this from the sum. Hold on, go get that back. The sum and difference rules tell us that we certainly are allowed to do this, to go from the limit of 4x plus 2 to 2 separate limits added together. And again, sometimes the motivation for doing this is to simplify what we're doing. If it's not necessary, then, don't bother. But sometimes breaking it up into pieces like this can be very, very helpful. And we'll see many examples of that today. But for this one, it doesn't really matter, but it's just important to know that you can do this. And then, of course, we can bring this 4 outside, okay, because it's a constant. Over here, this is a constant. So this first expression, we're going to wind up with 4 times the limit of -3 plus the limit of 2. And now these are all constants. So this is just -12, this is just 2. And they end up equaling -10. Just like we saw earlier, right here. Now, this one is a little trickier because remember, we have to watch out for the possibility of division by 0. But if you look very carefully, you'll see that that's not really going to happen because we're going to plug 2 in here for x. So we don't have to really worry about that. So what we could do then, because that's not going to be a problem, is we can directly plug in the 2. Oh, I'm going to run out of space for sure. I'll move it up here. Okay, so because we don't have to worry about division by 0 or taking the square root of a negative number, we can go ahead and just plug in the number 2 for all the x's, and that will, of course, give us our result. But we also can break it up into all the different components, which in more complicated cases may give us the ability to cancel out some of the terms, which would be one reason for splitting it up. Here, that isn't really necessary, but if we did, this is what we would get. Okay, so 2 times the limit of x squared minus 3 times the limit of x plus the limit of 1 over the limit of x cubed plus the limit of 4. Now we can go ahead and feel free to do all the substitutions. And of course, we'll end up with the same results we had before. Oops. Hold on. And it's exactly the same. All right, now the next one looks at first glance to be very, very complicated, but it really isn't. Whenever you see a radical sign, radicals always tend to make an expression look very frightening. So this is the next one. So, and once again, you don't have to worry about taking the square root of a negative number, because 6, when plugged in here, will give us a positive square root. So you could actually go ahead and solve this as 2 times 6. And so you're going to wind up with 11 times radical 10, and that's your answer. I have no idea what this function looks like. In fact, it might be fun to look at Symbolab and see what is going on with that. Hold on one second. Whenever the function really looks frightening, let's see what happens. So we have the limit as x goes to 6. Uh, 2x minus 1 times the square root of x plus 4. So they agree with us that it's 11 radical 10, and they're showing us that they just basically plugged in the values. The graph shows us that, oh, wow, that's interesting. It's not exactly what I was expecting, but yes. So when we have x equals 6, you can see way up here, and in fact, it's even labeling it for us. The limit is 11 radical 10. So the Symbolab is trying to be as helpful as possible. It's got other stuff down here too, if you ever want to check it out. But at some point there's some point you reach where you have to start paying for all the extra goodies, but it can do an awful lot before you have to start paying for it. Oh, see, that's what I thought. Yeah. The more you need it broken down for you, that's where it starts to cost you money. Yeah, that's what I thought. Still, it's a very valuable tool considering that it's free. Man, I didn't even know this was here. Look at this. It's just summarizing all the properties that we just went through. Look at that. They're all there. How do you like that? Okay. Well, anyway, so now what if we chose to break this up into individual pieces? Well, this is something we could have done instead. It isn't very different. You're just using the product rule. But again, sometimes breaking it up into pieces can help us simplify the expression, and then you should do this. Otherwise, it's not really worth it, but it's good to know that you can do it both ways. Now, here's an interesting one: polynomials and rational functions. What about their limits? Okay, well, Of course, a rational function is a ratio of two functions. So if we are taking the limit as x goes to a of this ratio, we're going to wind up with p of a over q of a, providing, of course, that q of a is not equal to 0. And once again, it is really just direct substitution. Now, it's possible, as we saw earlier, that this ratio p of x over q of x can be simplified, or we can just evaluate it directly like this. So here's a good one. Now, again, if you notice, if you plug in 0 here in the denominator, we will not end up with the problem of division by 0. So it would be a simple matter to go ahead and plug these in. Well, that worked out nicely. Almost all the terms are zeros. So it very simply reduces to 5/4. So I'll tell you what, let's check this out with Symbolab. There's got to be some value, though, that could cause division by 0. It's just not 0. So let's take a look at this. What do we have here? The limit as x goes to 0. What is it? 3x cubed minus 2x squared plus 5. And then we have 2x squared minus x plus 4. So, of course, we got the same result, and they're telling us here that you just can plug in the 0 and you'll get that answer. Let's take a look at the graph, though. By the way, oh, here we go. Now that's interesting. So it looks like there is no point where it has division by 0. Interesting. So, so there's our limit that we just calculated. When x equals 0, the limit is 5/4. That's this point. Huh. And you can see it's a cubic function because of the way it curves. All right, anyway, but the other option we had was to break it up into individual pieces. And of course, we still would have wound up with the same exact result. Okay, so here you would just plug in 0 for all the x's, and you can see you're still going to end up with 5/4. All right. Now, this is where it gets interesting. What if we have a case like this? Let me just show you a graph for a second. What's going on here? Well, this function seems to have a hole in it. The function is undefined at that point only. For whatever reason, it's undefined right there at that point. Now, what does that mean? Does that mean there's no limit? Well, let's find out. It turns out there's a very interesting result here. If we have two functions that are identical for every x except possibly x equals a, then they have the same limits when we take those limits approaching that point A. In other words, if they're the same everywhere except at A, when we take the limit as x approaches A, they still have the same limit. So now that is a very powerful result. It's going to help us a lot because it's going to save us. There will be many cases where you think, oh no, we don't have a result here. And yet it turns out that we do, as long as there's another function out there somewhere that's identical everywhere except at that point. So how does that help us here? Let's take a look at an example. By the way, I don't know, in a lot of results in calculus, they may have names attached to them. I don't think this one does. You might know from having previous math classes, we have theorems and we have lemmas and we have all these different results. I don't think this one has a particular name, but let's take a look and see how this will work. So we'll start with this function, x squared minus 1 over x minus 1. We want to know the limit as x approaches 1. Well, we know that there's a problem here. When x approaches 1, we have 0 in the denominator. And that means that at that point, the limit is undefined. We can't have division by 0. At that point, the limit would just be undefined. By the way, let's take a look at the graph in Symbolab. So it's going to be y equals x squared minus 1 x squared minus 1 over x minus 1. So if you notice, the domain is all values of x except for 1, of course, because that leads to division by 0. So when we go to graph this, now this is interesting. The point 1, 2 is undefined. There's a hole there because that would lead to division by 0. So what do? Do we stop and conclude that this function does not have a limit? Well, you might think so, but that's actually not correct. What can we do instead? Why don't we do some algebra, and we'll take the x squared minus 1 and rewrite it as x plus 1 times x minus 1, and then the 2x minus 1's cancel, and we're left with x plus 1. So basically, if we let that represent g of x, the f of x is the one we just saw. There's a hole in it. Actually, let me fix this. G of x is x plus 1. What would that look like? Okay, not the best drawing in the world, but you can see it's exactly the same with one major exception. It's defined at x equals 1. So it's the same except g of x does not have the hole. So because of that, when it comes to g of x, the limit is easy. The limit as x goes to 1 of g of x is 1 plus 1, which is 2. Okay, because we define g of x as x plus 1. So here's why this matters, because we said earlier that if these two functions are identical everywhere except at that one point, then they both have the same limit at that point. So this, all of the bottom line to all this is that the limit as x goes to 1 of f of x in spite of the whole is 2. Okay, so there's the whole doesn't have to be a problem for the limit. Okay, it's the same as the limit of g of x, because again, they're identical everywhere except where x equals 1. Now, in terms of converging, I mean, you can see why this is happening, because as x approaches 1 from the left and as it approaches 1 from the right, the point they're getting closer and closer to is right here. So the limit is 2, because as they keep getting closer and closer to 1, they get closer and closer to 2, and that's why the limit is actually 2. But this theorem lets us prove that it is 2 because of the fact that g of x has a limit of 2. And so again, this is something that will come in very, very handy. You might see the hole in the function and think, oh no, we can't do this, but that actually turns out not to be the case. All right, now here's where it gets really bizarre. What if we try to calculate a limit and we plug in all of our numbers and we end up with a ratio of 0 over 0? Again, you might say, well, this is really not good. That indicates that there's no limit. Well, it turns out that there still might be a limit. Just the fact that substitution gives us 0 over 0 doesn't guarantee that there's no limit. It makes it a little trickier to find it, but there still could be a limit. So let's see an example of this. How about this one? Now, here's the interesting part. If you plug in that 3 everywhere here, well, you can see, oh boy, we have 0 over 0, just as we were afraid. What do we need now? Well, it turns out that if we do a little algebra, we might be able to reduce this using our rules that we learned earlier to reduce it to something which does not have 0 over 0. Okay, in other words, the whole point of using the rules here is to rearrange this algebraically so that it does not result in 0 over 0. So what possibilities are there? How could we rearrange this and get rid of that pesky 0 over 0? Well, let's see. Well, here's a possibility. What if the numerator and the denominator have a common factor? Well, the one in the numerator that suggests itself right away. Oh, wait, actually, let's write it like this. It's x times x minus 3. So the question is whether or not we can factor x minus 3 out of the denominator. Now, you might have forgotten how to do this, but there is a way we can check this. This might bring back some memories. You've got 2x squared minus 5x minus 3. We're trying to see if we can divide x minus 3 into it. We're going to use a technique which is similar to long division. And so we'll start by multiplying this expression x minus 3 by 2x. Let's put that here. If I multiply this by 2x, I get 2x squared minus 6x. Now I'm going to subtract that. And these cancel out. This becomes a plus. And end up with x minus 3. Now I can just use plus 1. And you can see x minus 3 times 2x plus 1 by using FOIL. is 2x squared x minus 6. Oh, wait, I did something wrong there. 2x squared x minus 6x, sorry. Inner is minus 6x, and then last is minus 3. So if you add those up, you get 2x squared minus 5x minus 3. So that means we've done this correctly. Okay, so in other words, this expression could be rewritten very easily as and so now we have the limit as x goes to 3 of x over 2x plus 1. Now we don't have any problems. We don't have to worry about zeros, do we? No. So get 3 over 2 times 3 plus 1. We ultimately end up with 3 over 7. So there you go. So in other words, when you end up with 0 over 0, it's really just a question of looking for ways of simplifying the expression so that something that we don't want in there drops out. So here, even though substituting 0 in the original expression gave us 0 over 0, just by a little bit of algebra, we were able to reduce it to a form that does not have that problem. And so we can directly solve for it, and we end up with 3 over 7. So when we started out with 0 over 0, we may have thought, that's it, lights out, the game is over. No, by doing a little algebra, we were able to reduce it to a result of 3 7s. Now, it's not always going to be obvious. There's several things that we could potentially try to get our ratio reduced to something simpler. So we're going to see a few other examples here, like here's one. This one looks like a nightmare. Why? Well, the square roots always look scary. So what are we supposed to do with this one? Well, if you plug in the zeros, the negative ones, you're going to wind up with oh boy. You can see already that the denominator is 0. 0 over 0. And there's no way we can factor. There's nothing to factor here. So now what do we do? Well, we're going to use something that's very, very clever. And this, for this, we're going to do a little reviewing of it. Very important concept. Let me just jump ahead to that slide so you can see what we're going to do. We're going to review something called conjugates. And so anytime you have two what are called binary expressions or terms, this, by the way, means that there are two terms in two terms. And so if we have, for example, 3x plus 1, its conjugate is 3x minus 1. They're identical except for the sign. Same thing here, x squared plus 7, x squared minus 7. These are called conjugates of each other because they only differ by the sign. And the same thing, of course, here. And if you were exposed to this, just as a quick reminder, you may have also been introduced to the concept of complex conjugates. So a complex number is written as a plus bi. Its conjugate, its complex conjugate would be a minus bi. So it's the same idea except applied to complex numbers. Anyway, here's the beauty of conjugates. and why we often use them to simplify results. For any two conjugates, let's say it's a plus b times and a minus b, if I multiply them together, I'm going to only have two terms, a squared minus b squared. I don't have any terms in the middle. Like, for example, x plus 2y, x minus 2y. If you use FOIL here, x squared, outer is minus 2xy, inner is positive 2xy, and last is minus 4y squared. So these two are guaranteed to cancel each other out as long as these are conjugates. And so we would end up with x squared minus 4y squared. So in other words, this squared and this squared, we subtract them from each other, and this is our result. And this kind of thing can often end up simplifying whatever problem we're working on, especially when there's square roots involved. So let's see, how would that work up here? What would be, well, yes, you can see here that the direct substitution leads to 0. What would be the conjugate of this? The conjugate would be this. Okay, so again, they're the same except for the signs. If I multiply these together, what's going to happen is I'm going to wind up with x plus 2 squared minus 1 squared, which means x plus 2 minus 1, or x plus 1. Now, you know that you're allowed to multiply any number by the ratio of any other number as long as that ratio is the same in the numerator and the denominator. So we're going to do that right now. So in order to simplify this, we're going to multiply both the numerator and the denominator by the conjugate of this expression. That way, we're not changing anything. We're turning it into something that's a lot more convenient. It may not look like it right now, but when we're done with it, we will not have to worry about division by 0. All right, so let's see what that turns out to be. So the numerators, if you multiply those across, as you saw earlier, you'll get x plus 1. So when you multiply this out, these, when multiplied together, give me x plus 1. Now, in the denominator, we have a bit of a mess here. We're going to have to multiply these out and see what we get. Well, actually, no, it's not going to be that bad. I'll tell you why, because these will cancel out. Now we're getting somewhere. So after that cancellation, we'll just have 1 in the numerator. In the denominator, radical x plus 2 plus 1. And you can see when we plug in -1, we will certainly not wind up with division by 0. What will we get? Plug in a -1, and ultimately this reduces to 1/2. So that's a lot better than 0 over 0, that's for sure. Now, we might be able to see this from a graph. If we take this to Symbolab, sometimes it's hard to tell us. If the function is messy enough, it's kind of hard to see it, but let's at least give it a shot. All right, let's get that old Symbolab going. There we go. So first, I just want to see what this thing looks like. Limit as x goes to -1. Radical, it's a ratio. radical x plus 1, sorry, x plus 2 minus 1 over x plus 1. Okay, perfect. All right, well, first let it do the calculations and then we'll take a look at the graph. So it ends up being a half, perfect. Oh, here it is, here's the graph. Now look at that. So we wanted to know the limit, here it is, when x equals -1, -1 comma a half. Now, this is the result of the simplification. The original function would have had a hole here. In fact, let's do this. Yeah, see, there's our hole. But we can see by using our cleverness, we were able to calculate and determine that the limit is in fact a half. And again, you can see that the function approaches a half from either side. Okay, so again, that hole doesn't represent a problem when it comes to calculating limits, as long as it's the same coming from both sides. That's the key. Now, just as a quick reminder, let me just draw a quick picture here. We'll see more of this in a few minutes, but if you have a function like this, the limit exists. Let's say this is a. But if you have something like this, because we have a gap in there, the limit does not exist. Because the value that the function is converging to is different coming from the left and coming from the right. That's why this is happening. So here, uh-oh. Oh, right. It happens to everyone. Don't you worry. I get it. No, when I was growing up, I was very young, your age. My house was very noisy too. It was very frustrating. So yeah. All right. So the recording should be ready later tonight, or if I forget, maybe first thing tomorrow morning. It has to be converted into MP4, and that can take a while with such a long class. So if you don't see it there tonight, you can watch it. I'll have it ready by tomorrow. All right, and see you next time. All right, so anyway, yes. So the point of all this is that the limit coming from the left and the right, in this case, are the same. In other words, x is coming from the left here, it's coming from the right here. In both cases, this is the value y that they're both approaching. It's the same, but here that's not true. So here the limit is different coming from the left and the right. And so therefore, the overall limit, the two-sided limit, does not exist. So that's why a single hole like that is not going to be a problem, as long as the function itself is continuous. Okay. Anyway, so here's another one. Oh my God, look at this one. So once again, if you plug in all the one for all the x's, another 0 over 0. What can we do? Well, here, there might be a different way of simplifying. What we would ideally like to do is have a single ratio in the numerator. That might make it possible to cancel something out. But how would we do that in this case? It's kind of a mess. Let's see what we can do. Let's focus on the numerator for a second. Ideally, we would like to convert this into a single ratio, which hopefully leads to a cancellation somewhere. So here's what we can do. How about multiply this one by 2/2, and we multiply this one by x plus 1 over x plus 1, because those are the denominators. Now, of course, this is, in both cases, all we've really done is multiply that term by 1, so we haven't changed anything. But the beauty of this is that you now suddenly have the same denominator for both ratios. And so you're going to wind up with, have a space already. 2 minus x plus 1 Okay, so that's our new numerator. Now, is that going to help us? That's a good question. Maybe. Now, here we have to be super careful with this thing, because the original function is this. Let me move this down here real fast. So we just got through determining that the numerator is 1 minus x over x plus 1. The denominator hasn't changed. Actually, I just realized I did not do this correctly. I left out the limit. Okay, hold on. So it appears at first glance that you can cancel, but actually not just yet. Because in the numerator up here, we have 1 minus x. Down here, we have x minus 1. So we have to make one more change here. Oh, sorry, wait. X minus 1. Now, this is the equivalent of negative x minus 1 So ultimately, the bottom line is you've got the limit of negative 1 over x plus 1. Okay, well, that was a bit messy, but
sorry, Professor, I feel like I missed this, but how did you go from 2 minus x minus 1 to the 1 minus, like the second part?
oh, all right, let's look at it one more time. In fact, I'll tell you what, it's all right here. Let me just show you what I did earlier. I spent a lot of time typing this up, so I might as well take advantage of it. So we've got the two terms, 1 over x plus 1 minus, this is still the numerator only. So we're multiplying the first term by 2 over 2 minus a half times x plus 1 over x plus 1. So when you multiply them out, they both have the same denominator, 2x plus 1. The first term is 2. The second is negative x plus 1. So I combine them into one term. So the denominator stays here. We've got 2. Now this minus applies to both x and the 1. So we've got 2 minus x minus 1, which reduces to 1 minus x over 2x plus 1. That's the numerator. Okay, now the denominator was originally x minus 1. So, yeah, so that's this part. This is what we just did. But the only unfortunate thing is that this 1 minus x doesn't cancel out with x minus 1. So what we can do is rewrite this as negative x minus 1 over 2 times x plus 1, all divided by x minus 1. And then this is where the cancellation comes in. So you basically have negative 1 over 2x plus 1. And now you can plug 1 in directly to this x without any difficulties because there's no possibility of division by 0. And when you do that, let me show you what happens on the next slide. Just plugging in the 1 means I've got negative 1 over 2 times 1 plus 1, or ultimately I have negative a quarter.
Okay.
All right.
Yeah, that made sense. Thank you. So
Okay.
are we like in general? Oh, sorry.
Go ahead.
So in general, with like all of these, are we just trying to like manipulate the problem until we're able to get the limit, unless the limit doesn't exist?
Yeah, that's pretty much the size of it. And the way you approach it will depend on what the problem is. Like here we've got 0 over 0. Later on, we'll see that you might have infinity in the numerator or the denominator. And then there are different techniques we can use to come up with an answer, although it may turn out that there is no limit anyway. But here at least, if we use algebra, we may discover that there is an answer in spite of the fact that we started out with 0 over 0. So yes, a lot of this is dedicated towards simply rearranging this algebraically to turn it into a more useful form. So yeah, I mean, that's really the bottom line. If there's no division by 0 or any other issues, then often direct substitution will give us our limit. But we will eventually run into some more complicated cases. Like, for example, you 0 times infinity or infinity over infinity. And that will require us to use techniques that we don't yet know how to use because we haven't introduced the derivatives yet. Okay, so for now, we're sticking with the ones that we can just simply solve by rearranging them.
Thank you.
There are more techniques we'll learn in chapter 3 once we understand derivatives that will make us able to solve even more limits.
Thank you.
Okay, so anyway, now here's another one. Now, I think we're getting pretty good at this. I don't know, maybe we don't really need so many more examples. Oh, what the heck, more examples are always better. Like this one, now it should be pretty clear that if you plug in these numbers, these negative 3s, we'll get 1 over negative 3 plus 2 plus 1, all divided by, oh boy. Yeah, we're in trouble. All right, so what can we do? Now, I would, right off the bat, I would say that we're probably going to combine these two by creating a common denominator. But because only one of these two is a fraction, we really only have to worry about the 1. So let's focus on the numerator now. So we can always multiply any number by a ratio. Where the numerator and the denominator are equal to each other. So here, this is our numerator. And so let's try 1 can be multiplied by x plus 2 over x plus 2, because we want that same denominator. And so we end up with the same denominator. We combine the two numerators. We have 1 plus x plus 2. So ultimately, this is our final result for the numerator of that expression. So now we put that back into the original limit. Remember, it started out like this. So we're going to replace the numerator with x plus 3 over x plus 2. And you'll see that actually makes things a lot simpler for us. So it reduces very nicely to 1 over x plus 2, and then the negative 3 goes in here, and we end up with 1 over negative 1, which is just negative 1. All right, there's one more example of this here, and then we're going to try something a little different. This one's kind of fun because we have division by 0 twice. We don't actually have 0 over 0, but as long as we have division by 0, we still need to do something to rearrange it algebraically to get rid of the division by 0. So here, if you plug in the 0, oh boy. You'll just end up with 2 divisions by 0, which of course we can't have. So we're going to try again to come up with a common denominator for these 2 expressions, which shouldn't be too difficult, since they already have one term in common, which is the x. So let's jump ahead and see. So actually, let me do this. Let me copy the original limit here so we can see everything together. We started there, and so we're going to multiply just this first term by x minus 5 over x minus 5. And that leaves us with x minus 5. These two I'll combine to come up with this expression. The common denominator is just x times x minus 5. So this reduces to x over x times x minus 5, and these cancel out very nicely. Yeah, this is working out very well, I would say. And then you just end up literally with 1 over 0 minus 5, which is minus 1/5. All right, so now we're going to do some slightly different techniques. Oh, and then we're going to introduce some interesting theorems. We have theorems in this chapter. Now, the theorems that we see here are really nobody's going to ask you to prove anything. That comes down the road. If you're majoring in math, eventually you'll start proving theorems. Most math departments will have, let's say, 3 semesters of calculus, where it's just all calculating things like we do here. If there's a 4th semester of calculus, it would usually be called something like advanced calculus or possibly real analysis. And that's when you really start proving everything in sight. So we're not going to do that here, but as we run across these different theorems, we're going to at least try to understand what they're telling us and what they could potentially be used for. And in some cases, these theorems are helpful for finding, let's say, limits in cases where it might otherwise be terribly difficult. Like there's one in particular that will come in handy when solving for trig limits. But we're not going to try to prove anything. We're just going to learn about these theorems, and they'll come in handy again down the road when you start learning about proofs. But for now, we just want to introduce ourselves to them. There's 2 of them in this chapter, the so-called squeeze theorem, it's called, and then the intermediate value theorem, which are very important for material that comes down the road. But here our focus is really more on computational issues. And so anyway, so I think it's time for our first break, or our actual break. What we're going to actually do when we get back is we're going to see how sometimes we may only want to evaluate the limit of a function from either the left or the right. Okay, sometimes that's all we need. So, and then we're going to look at how to evaluate limits for piecewise functions. And then we'll get to see this squeeze theorem and see what that's all about. And then in the next section, set 2C, continuity. We're going to have to introduce this discussion about continuity. Continuity proves to be incredibly important in calculus. And we want to understand what continuity is, but we also want to understand what happens when we do not have continuity. We have instead what's called a discontinuity. And it's kind of theoretical, but it's awfully, awfully important. It lays the groundwork for what comes later. So yeah, we'll have some theory tonight. But now, by the way, when we're done with all this, we'll be ready for chapter 3, which is our introduction to derivatives, which really, to me, is the heart and soul of the whole course, because a lot of the material is based on derivatives. There's a lot of techniques we need to learn, but they're so, so useful in so many applied areas. So today's Tuesday. We'll probably get to that on Thursday because we're getting close to the end here. Even if we don't quite finish chapter 2 tonight, we definitely will have it ready, finished by Thursday. And then we can dive into derivatives, which I think you'll agree when we see them that it is really very, very interesting. And certainly it's very useful. But in the meantime, let's knock it off for a bit. And when we get back, we'll start looking at one-sided limits again and piecewise functions. All right, so see you all in a while. Okay. All right, so sometimes we may want to just simply evaluate limit from one direction. Now, here's a good example. Let me see if I can get the graph. So you can see why you'd be tempted to do this. Radical x minus 3. Well, anyway, so the bottom line here is the domain of this function, radical x minus 3, is everything from 3 up to infinity. So it wouldn't really make any sense to try to calculate the limit from the left because the function is not defined for any x below 3 on the graph again. So in other words, you don't want to be coming from the left to calculate the limit, but instead, this way you only need the one-sided limit to determine. Now, of course, you can see where this is going to happen. This function will cross the horizontal or touch the horizontal axis at 3, 0. So when you solve for the limit, from you'll not want to. So okay, so let's try that again. So the function's domain starts at 3. So to try to calculate the limit from the left isn't going to work because there are no values of x below -3 that are in the domain. The limit would just be undefined. But coming from the right is a very different matter. If you plug in 3 into this function, you'll see that you'll end up with 0, which simply means that if you look at the graph again, you can see as x approaches 3 from the right, eventually the function reaches 0, okay, the point 3, 0. So we have, in this case, only a one-sided limit. The limit from the right is equal to 0. The limit from the left is undefined. Okay, now here's a bizarre case. The piecewise function. That means that it has 2 distinct regions with very different behavior. Now, let's see. I think it's possible to graph this in Symbolab, but I don't remember exactly how. I have to look it up. Oh, there you go. Okay. I didn't know this was here. I actually still don't know how to do this without going to Google, but it's here. So let's take advantage of it. I just want you to see what this thing looks like. So we have 4x minus 3. Hold on. I actually have 2 different Symbolabs open now. 4x minus 3 when x is less than 2. And x minus 3 squared everywhere else. Okay, so when x is greater than or equal to 2, the function equals x minus 3 squared. All right, so let's take a look at this thing. Now that's a bizarre function, okay? But you can see that there are going to be 2 different limits coming from the left. The function will not go above 5, okay? Coming from the right, it appears to be converging to 2, 1 rather, okay? So let's just prove that by calculating both one-sided limits. So coming from the left, meaning this section, when you plug in 2, you end up with 5, okay, which is what we'd expect from here. It actually says so right here. Now, remember, we have a hole here, but we've seen already, this is still the limit from the left side, okay? the fact that there's a hole there doesn't stop it from having a limit, because as we get closer and closer to 2 from the left, the function gets extremely close to 5. And so that is the limit. Coming from the right, when we plug in 2, we end up with 1. Now, of course, as we've already seen, when we have a limit from the left and a limit from the right, and they're not equal to each other, that means the two-sided limit, the limit of the function, is undefined. Okay, so it has two one-sided limits, but it does not have a limit for the entire function. All right, now this squeeze theorem. Now, the purpose of this thing, it's going to seem very bizarre and abstract, is to find the limit of a function that is in between two other functions within a given region of the real number line. So like here, you can see the way they've drawn this. You've got f of x and you've got h of x. So if it turns out that they both have the same limit at a given point. Oh, by the way, I went right over this slide. It must be true for this squeeze theorem to work that these functions are such that no matter what the value of x is, f of x is the smallest. It's always the smallest of the three. G of x is, well, let's say h of x is the largest, and g of x is always in between the two of them. And you can see they do not ever cross each other. So in other words, no matter where x is, f has the smallest value, h has the largest value, and g is always somewhere in between. And when that happens, we can take advantage of this at that point A. If the f of x and the h of x both have the same limit, which we'll call L, that means the g of x must also have that same limit L. It's squeezed in between the two. I guess that's the origin of the name. Now, you're probably wondering, when in the world would this ever come in handy? Well, some of these more complex results are really designed to help us with trigonometric limits, because these can be extremely complicated to deal with. So the example we have here is the limit as x approaches 0 of x times the cosine of x. Okay, now ordinarily, if you were to plug these numbers directly into this function, it turns out you'll just wind up with 0. Okay, so we already know before we apply the squeeze theorem that the limit of this expression is 0. But let's see how we can use the squeeze theorem to determine this. Now, the diagram here is really messy. Here's what they want you to see. The cosine, remember we saw that yesterday. Let's actually go back here and look at the graph of x cosine x. Yeah, it's quite a mess. So they've chosen the region in here. Is the dark blue line is x cosine x. Cosine x, though, let's go graph that again. And we did that yesterday. Let's just take one more look at it. Has an interesting look because it repeats itself on a regular basis. In other words, it just keeps going through these endless cycles. And at no point does the value go above 1 or below -1. So the range is the values between negative and positive 1. So that means that no matter what the value of x is, the cosine is bounded between -1 and +1. Well, now it turns out that the cosine of x and the cosine of absolute x actually are the same. They always give us the same results. So the squeeze theorem tells us that what we can do now is basically claim that the cosine of absolute x is always bounded between negative and positive absolute x. And that being the case, we think of this as our f of x, our g of x, and our h of x. And we solve for the limits of these two absolute values, they're both zeros, as x approaches 0. That guarantees that the limit of cosine of x is also 0. And so therefore, when we plug that into this formula, we're guaranteed to get a 0. Okay, so anyway, obviously we're not going to use this theorem unless it's absolutely necessary, because it's quite a mess, but it's just simply a way of, it's a theoretical way of finding limits when there may not be any other ways of going about it. Okay, so, but luckily for us here, direct substitution will give us the answer we need anyway. But if not, then one of the techniques we might try, especially with trigonometry, is the so-called squeeze theorem. But anyway, so now we're ready to start looking at continuity. So continuity is actually a very straightforward concept. In fact, I remember one of my math classes, the professor said, if you can draw a function without ever taking your pen off the paper, then it is continuous. Okay, in other words, it just simply means there are no breaks or gaps in the function. Okay, so in other words, y equals x squared is continuous, because I can draw it. I'm trying to make it look just right. It's continuous because there's no breaks or gaps in the graph, whereas something like this is discontinuous because there's a hole there. It's not defined at this point. Okay, so this function is continuous. And this one is not. Now, as it turns out, there's more than one way of being discontinuous, and we're going to see all three of them. But this is an easy one to explain. Just the mere fact that something is missing makes it discontinuous. Now, by the way, sometimes even with these discontinuous functions, you might see something like this. So let's say this is y equals x plus 1. And this is just a single point, 1, 2. Actually, sorry, 1. No, that can't. No, I've done something wrong. Let's try that again. Okay, so in other words, there's a discontinuity in there, but this point actually represents f of 4. So in other words, this function could be defined something like this. It's technically a piecewise function because it's y equals x everywhere except where x equals 4. And at that one point, it's actually equal to 6. So there's a discontinuity in it. But even though there's that extra point up there, because I had to take my pen off the paper to draw that, we can think of it as being discontinuous. Now, in a case like this, there's not going to be a limit either, because the value is different from f of x, but where there is a point here that fills in the hole, so to speak, but the function is still discontinuous. Now, some of these graphs are so nice in the book that I just borrowed them basically for the notes. This is what it looks like when there's a hole. And of course, this would have been f of a had it been continuous. So this is one example of a discontinuous function. But like I said, there's more than one way of being discontinuous. Here it's because there's a hole. In other words, the function is undefined at that point A. But what about this one? So all of a sudden, you can see there's a gap. There's two different sections of this function. Now, here the issue is that the limit does not exist, because the limit as x approaches from the left is different than the limit as x approaches from the right. Okay, so let's just say, to make it easier, this is 4 and this is 6. So the limit of this function as x approaches a from the left is 4. The limit as x approaches a from the right is 6, and they're not equal to each other. So therefore, there's no limit. And in addition, the function is discontinuous. So in other words, here the reason why it's said to be discontinuous is because the limit at that point does not exist. Even though f of a is defined, that was the problem in the previous case. F of a was not defined. Here it is, but we still have a discontinuity because the limits are different coming from the left and the right. Okay, so here I've written it again. Even though the function is defined at a f of a, the fact that the limits are different from the left and the right means that the limit is undefined. And that tells me that f of x is discontinuous at that point. Now, the third one is the one I was just showing you. Here, the problem is that while f of a is defined, the problem is that f of a is different than the limit as x approaches a from either direction. And so when these are not equal to each other, again, we have a discontinuity. So there's really three ways we can have discontinuity. Now, by the way, all of these formally are known as being, we're referring to something called continuity at a point. It turns out that continuity can be defined at a single point or over an entire interval. So all of these represent being discontinuous at a single point. Okay, this one is continuous. This one is discontinuous, but specifically we mean at a single point. Anyway, just to wrap this up, continuity at a point requires all three of these conditions to hold. F of x is defined at x equals a, and if it doesn't, we have the whole case. The limit exists. If not, we have something like this. And then here, we have the whole. We do have f of a, but the limit is not equal to that. Okay, so there's the three possible cases where we find that the function is not continuous at a point. Okay, now it turns out some types of functions, we don't have to worry about this. For example, polynomials. Polynomials are nice. They're very well behaved. One of the great things about polynomials is that they're always continuous because it's never possible to run into those problems we just saw. Okay, so remember what a polynomial is. Let's see, let me write down the general expression here. So, for example, a cubic function is a polynomial. And so we know that polynomials are well behaved. There's never going to be a case of division by zero. There's certainly not going to be any issues with taking square roots of negative values. So polynomials are always going to be continuous. Rational functions, on the other hand, are always continuous unless the function in the denominator equals zero. Okay, so like here, for example, we have f of x plus 1 over x minus 5. The problem with this function is that the limit, as x goes to 5, well, it's not going to work. Okay, let me show you a picture. Oh, here it is. Here's the picture. So you can see that when x equals 5, the limit from the right, let's say this is a is 5. In fact, this limit is infinity. And the one down here is negative infinity. And since they're not equal to each other, the limit does not exist. Okay, so the function is clearly discontinuous. And the existence of this vertical asymptote tells us that this function is not continuous. But many rational functions are continuous. But again, when we take the limit, if the denominator is 0, that means we have a discontinuous function. Now, the discontinuities actually have names. Okay, I just want to throw that in there. The three basic types that we just learned all actually have names. The first one, the removable jump and infinite discontinuities. What do they mean? Well, removable basically means that if you could define one more point, you'd be continuous. So this one, yes, removable discontinuity is the case where f of a is different than the limit. Okay, so it's like there's a hole, but there's a value for f of a anyway. In other words, f of a exists, but that's not good enough. But we have this problem. The jump discontinuity is where the function is actually in two distinct pieces or segments. That would be this case. And of course, the problem here is that the limits are different coming from the left and the right. And then the case where we have a vertical asymptote is called infinite discontinuity. And again, the problem here is that the limits can't be the same because one of them is negative infinity and one of them is positive. In this case, this one is infinity. This one is negative. And because they're different, that implies that the limit does not exist. Okay, so those are the three basic types of discontinuities. Now, the reason why this matters so much is because the properties that we want to take advantage of will often depend on a function being continuous. In other words, some results that we'll need are only defined for continuous functions. Derivatives, for example, require continuity. So it's important for us to know right away if a function is continuous or not. Okay, before we try to do anything with it, it's very important to know whether or not it's continuous. Now, here's an interesting question. Suppose I gave you a function and said, well, we know that this function, if we try to take a limit, we're going to have a problem. Division by 0. Oh, whoops, sorry, it's 2. In fact, it's our old friend 0 over 0. Now, what we're being asked here to do is not find the actual limit. What we're trying to do is determine what kind of discontinuity this is. Okay, so if you look at it carefully, you'll see this is the one with the hole. And so as we've seen many times before, we can find this limit if we take our original expression and rearrange it algebraically. So I factored x squared minus 4, which you can double check with FOIL. These drop out. And so the limit is in fact 4. And you can tell just by looking at the graph, it would have to be 4 because it's the same coming from both directions. Whether x is increasing or decreasing, function is converging to 4. But we know that f of 2 is undefined, but the limit approaches 2 is defined as a whole. This is an example of a removable discontinuity. Okay, so in other words, these are the two basic times when we call this removable, this case and this case. Either way, the problem is the whole. Okay, so removable discontinuity, you can think of that as the case where there's a whole, even if there's another value there, this still qualifies as a removable discontinuity. All right, now, our favorite, the piecewise function. So what happens here when x equals 3? Well, we don't have to worry about division by 0. The problem, though, is that if you look at this graph, well, you can see there's a problem here because when x approaches 3, the limit as x approaches 3 from the left is 5. Actually, let me try that again where there's more space. And up here, as we get closer from the right, this is 4. So they're not equal to each other. So the limit does not exist. And that's the jump discontinuity. In other words, it jumps directly from here to here as x approaches from the left or the right. All right, so just a couple more theoretical results, and then we'll be done with this topic, and then we can move on to derivatives. Although when we start out with our derivatives chapter 3, we will introduce, or we will define them in terms of limits, and then we basically won't need them again for a while. I did say before that we can define continuity at a point, which is what we've been focusing on, but we can also define something called continuity over an interval. Okay, so basically, what is that all about? Well, there's 2 basic cases. We have a function can be continuous from the right at A. Let's say A is 3 and f of A is 2. It should be clear that as we approach from the right, the function has a limit of 2, and f of A is also 2. So since they're equal to each other, this function is continuous from the right. If we had something like this going on, well, then they would not be, because the limit would be here. The limit doesn't exist. That's why the limit doesn't exist. Not only do these not equal each other, the limit does not exist. That's what I should have written. Okay. Then we also, of course, can have continuous from the left. So as x approaches from the left, we get to this point, the limit, as x approaches 3 from the left, is 2. Well, we also know that f of 3 is also 2. Therefore, the function is continuous from the left. Now, here's an interesting result. What we're going to do here is look at this function, and we're going to basically just try to determine the intervals over which it is continuous, if any. Okay. So let's look at this thing. First of all, when you see this graph, you'll say, oh my God, what is going on here? It actually has 3 distinct sections and 2 vertical asymptotes. All right, so let's take a look at this graph. Oh my God. So where are the vertical asymptotes? 0. And it's hard to tell from this little piece that I copied, but it's 0 and -2. So basically, though, you can see that the function is continuous everywhere from negative infinity up to, but not including 2. It's continuous in this range from -2 to 0, but not including either one of them. And then here, again, from 2 to infinity. So it's actually continuous everywhere except for those 2 points, -2 and 0. Then we have the the infinite discontinuities. But you can technically write, you could write it like this. This is the range within which it is continuous. It is obviously discontinuous when x equals -2 and when x equals 0. All right, so we've got 2 more theoretical results. I just want to quickly show you. And then on Thursday, we'll just pick it up with chapter 3, where we get to look at derivatives at long last. So this next one is called the composite function theorem. And basically what it does is it shows us a quicker way of calculating limits for a composite function, f of g of x. Okay, now here, as always, there's multiple ways of doing this. Now, this result is going to look terribly scary, but it really isn't. When you see how simple it is, you'll say, oh, that's not a problem. But we need to have an example to really understand what this is telling us. So once you see the example, you say, oh, what's the big deal? Okay. In fact, I'll tell you, let me copy this onto the next slide so we can keep an eye on this. What exactly are we trying to demonstrate here? Well, I've chosen a very simple example. F of x is x plus 1. G of x is x squared minus 7. So you recall from the beginning of the class, this is when we create a composite function, what you're basically doing is replacing all the x's here with g of x's. So that works out to be x squared minus 7 plus 1, or very simply, x squared minus 6. The limit of just g of x as x approaches 3 is 2. Okay. So what is this helping me do? What is the limit of f of g of x it's f, oh, by the way, this is L. So that means it's just f of 2, which is x plus 1, 2 plus 1, which is 3. So, I mean, this is a very simple example, but it can speed things up when you're trying to calculate the limit of a composite function. If you are able to apply the limit to the g of x and then use that information to come up with the limit of the entire function, just by plugging in the 2 into the f of x, that's all we need to do. So that the purpose of this is just to make things a little simpler with composite functions. Now, there's an intermediate value theorem. This is something that you should have heard of, but nobody will ask you to prove it. I don't think we're actually going to use it. Not yet, at least. But just so you're aware that this function or this theorem exists. And so the wording of it is horribly, horribly complicated. Let me just show you the graph so you can see what this is all about. What they're basically saying is that if the function is continuous between a and b, which it is, okay, here's a and here's b, then we know that if we pick any value between these two, there must be some value between a and b which is associated with that. In other words, just the mere fact that z is between these two values guarantees that there is some C in the real number line. Such that f of C is equal to Z. So again, it's like, well, all right, that's fine, but we're not really going to put this to use right now, but it's good to be aware that this exists because it might help us identify a limit for a much more complicated function. Okay, so just for now, just be aware that this theorem exists. We're not going to actually use it again anytime soon, but you might run into it in a more advanced calculus class. So it's good to be aware of these theorems. Eventually you'll need them all, but for now, it's enough to know how this thing works. Now, the derivatives, you can see right off the bat, the derivatives are actually defined in terms of slopes. But as we saw the other day, we're aiming for a tangent line, but that tangent line is actually the limit of secant lines as the two axes get closer to each other. So this we've already kind of seen before. We saw an example of this yesterday. We're defining this rate of change of a function by taking secant lines and getting them closer and closer to this tangent line. So we're basically taking a limit. But here we're going to take that and run with it and use it to define the concept of the derivative. Okay, so we do need to remind ourselves how limits work. But they'll be applied to relatively straightforward functions, but we do need to remember how limits work in order to understand this definition. And once we understand the formal definition of derivatives, after that, we can basically focus our attention on the rules. Okay, and there's a lot of rules. There's quite a few rules of differentiation, as they're called, but this is, like I said, this is something that's going to prove to be extremely useful in applied areas. Unlike limits, limits are really a theoretical construct that helps us understand what derivatives are, but the derivatives that we're going to learn about here are going to be very, very helpful no matter what you're majoring in. Somewhere along the way, derivatives will get involved. And we'll be using it for a lot of interesting things like, for example, optimization problems. Imagine the company's trying to figure out the maximum number of products they should sell, or sorry, the optimal number of products they should sell to maximize their profits. Well, that is going to be calculated with derivatives, okay? So there's a lot of derivatives in economics in particular, but you'll see them in many other disciplines, especially if there's optimization involved. And of course, you know that Newton invented calculus. This is what he was aiming for. He was trying to explain the motion of planets and other astronomical bodies. And so we're getting into the really important, really useful things here. It's still kind of theoretical, but finally we get to do things that are also very practical. So anyway, but we'll have to stop it right here, and we'll have to save this until Thursday. So in the meantime, as soon as the recording is ready, I'll post it and you can watch it if you want to. And on Thursday, I'll also post another assignment. So don't forget, try to get your first assignment in by Thursday night, and then we'll take it from there.
I had a quick question.
Yes, go ahead.
How do we submit the assignment?
Oh,
Because I was trying to look on the syllabus and you didn't.
You know what? I'm so low tech. You know what? This is what I've been doing. I've been having people take and write this stuff on a piece of paper like you normally would in a classroom setting. And then you can either use a scanner or scanner software, or else just take your camera on your phone and just take pictures and just email it back to me. And so far it's worked pretty well.
Okay.
If you're going to use your camera though, just make sure that it's legible. Take a look at it before you send it to me, because if you can't read it, I can't read it. But so far it's worked fairly well for me.
And
Very
this is
occasionally,
a Gmail
yeah,
email?
Gmail, the same Gmail account we get your invitations from.
Okay. All right, thank you.
I was wondering when our first exam, just because it's not on the syllabus.
Oh, I don't know. It's hard for me to predict. The thing is, when it is time to have an exam, I'll give you at least a week to do it. So we'll practice, like we'll come to a point and we'll say, all right, that's it. It's time to have an exam. So then what we'll do is we'll have some more practice problems to go over to get ready for it. And then I'll post it. And then I'll give you, let's say, a week to get it done. So see, the problem is it's hard to predict with, it's not only is it the summer, but we're doing this online, and that makes it doubly hard to predict when we'll be at that point where we're actually ready for the midterm and the finals. So, but be aware that you'll have plenty of time to get it done. Now, if you are going to be, well, the class ends something like August 1st or 2nd. Probably it would be due. Well, I'd have to look it up, but you'd have at least a few days after that. So what would happen in that case is I'd post it, let's say, the week before our last day, and then I can give you like up to, let's say, a week or even 10 days to get it done. I can't be more specific than that, but I do know that whatever is the last day of our class, the grades have to be in typically 3 or 4 days after that. So, and I want you to have at least a week to get it done. So most likely I would post it maybe a week before the semester ends. And then you'll have, like I said, anywhere from 7 to 10 days to get it done. So that's the best I can do. Sorry. In a normal classroom setting, you're in the class, it's the fall or the spring, it's 16 weeks. It's very easy to predict these things, but this makes it very difficult, much more difficult. So, but as we get closer to the day, I'll let you know what's going on. Now, if you're planning on going away somewhere, or if there's an actual issue, a genuine problem, like, well, I have to move out of my apartment because it's the summer now, or, things that will interfere with your getting this done, just let me know. And I can arrange for you to have extra time if I know about it. Okay. Or if you've already arranged to have a vacation, let's say, during that same week, we can figure something else out. I don't want this to be a problem for anyone. So just let me know if there's something that would, let's say, make it difficult for you to get the exam done in time. As long as I know about it, it's not a problem. So don't worry, you'll be fine. Okay, 1 year, believe it or not, this shows you how sometimes you never know what's going to happen. At a different school, no, it wasn't a different school, it was this school. What am I talking about? For one of my in-person classes, I had to give one of the students the exam a week early because he already had signed up to be in a movie in South Africa. So he had to catch a very specific flight, and that was it. He had no other option. So I had to give him the exam earlier than I normally would have, because otherwise he would have missed being in the movie. So you never know what's going to happen. All right. So yes, but it's obviously going to be somewhere in the middle of the semester, but I just can't be more specific than that right now. All right. Anything else? Okay. Well, then I guess I'll see you all on Thursday then.
Thank you.
Okay. All right. Good night.
Bye.
All right. Bye.